Hello, today I'm going to talk about automating quick interoperability testing. I am Martin Seemann and I work at Protocol Labs, and I'm going to present the QUIC interop runner, which I developed in collaboration with runner Ian Garr from Fastly. Why do we do interoperability testing? Well, first of all, obviously, we want to make sure that QUIC implementations developed by different vendors work well with each other. But there's a second reason we do interop testing. If there are some points in the specification that are less clear than they could be, different implementers will make different assumptions about those points. And those assumptions might clash in interop testing and lead to test failures. We can then use those failures to inform the work on the specification itself. This is why interoperability testing has been a part of the IETF standardization process for a long time. Here you can see the QUIC interop matrix, which was generated for the IETF 108 meeting about 2 weeks ago. To do that remotely, people usually set up a QUIC server on a public endpoint on the internet and then publish the IP address and port so that other people can use their QUIC clients to connect to those servers. As you can see, there are more than 15 implementations of the QUIC protocol now. That means that if you want to test the interactions between each and every one of them, you'd have to test more than 200 interactions. And since QUIC is quite a complex transport protocol, one test is not enough. You need to run about 20 tests to get a good coverage of QUIC's features. In fact, every letter in the table cells in the matrix is a test for one QUIC feature. Another problem is that both the QUIC client and the QUIC server are located on the public internet, and you don't know what kind of network conditions they experience. There might be cross-traffic, there might be packet loss, there might be reordering, but you're not sure of that. It's unpredictable for every test. Furthermore, tests are only loosely specified and the test results have to be interpreted by the implementer. For example, we used to have one implementation that only implemented the QUIC transport but not the HTTP 3 layer. But the implementer still wanted to have that shiny little 3 in their cell in the interop matrix. So what they did is that they took a pre-composed hello world HTTP 3 response and just shipped that every time the client opened a new QUIC stream without even pausing the HTTP request. Clearly, we need to do better than this. Let's automate things. So first of all, we don't want to run things on the public internet. We don't want to deal with unpredictable network conditions anymore. So what we need is a local client implementation, and we need a local server. And then to be able to control the network, we want to have some kind of network simulator in the middle. And we evaluated different options for this. We could have used NetM, but we wanted to have really fine-grained control. So we decided for NS3. In NS3, there's a real-time mode, which exposes a socket that can read packets and write out packets from the simulation. And then within NS3, we can manipulate the traffic as we want. For example, we can parse packets, we can drop packets, we can black out the connection. We can do whatever we want. There's a problem with running someone else's QUIC implementation locally, though. You first have to build it. And building someone else's code is usually not fun. It's probably written in a language that you're not really familiar with, and it comes with a bunch of dependencies that you first have to figure out. Furthermore, some implementations are not even open source, so building them locally is not an option in the first place. But what if we just use Docker containers and ask implementers to provide a Docker image of their implementation? They know how to build it, so it's easy for them to just write a few lines of Docker file to build a binary of a QUIC client and QUIC server of their implementation. This also solves another problem. It's not an easy task to prevent the kernel from routing the packets between client and server directly, but to force them through the network container. By using Docker containers, it's quite straightforward to set up the routing. Once we had that basic setup running, we thought about what tests we want to have on the interop runner. And the first tests we implemented were easy tests that we also did in manual testing. We want to test the QUIC handshake, we want to test the QUIC handshake using the retry mechanism, and we want to test session resumption at 0 RTT. These are quite simple tests, but it's valuable to automate them. But then we came across some tests that are quite difficult to perform manually. For example, we have a heavy stream multiplexing test. In this test, we expect the client to download 2,000 files from the server over a single connection. This is possible if you do it manually, but it's just very hard to set up, so people were not doing that on a regular basis. A test that proved to be very valuable is the packet loss and the packet corruption test. In this test, we just randomly drop packets either during the handshake or after the handshake. QUIC loss recovery is quite complex, especially during the early handshake phases where you have to run loss recovery over different packet number spaces. And there was not a single implementation that got it right when they joined the interop runner. They all found a bunch of bugs in this part of their code. There's another test that's now possible that we have a network simulator. We call them the benchmark test. The simplest test is just filling a pipe. In this test, NS3 simulates a fixed bandwidth, fixed RTT pipe that has a finite queue size. And when this queue fills up with packets, it starts dropping packets. The congestion controller of the QUIC implementation would then pick up the signal from this packet loss and scale down the send rate. In this test, you can see if a congestion controller of a QUIC implementation can determine the bandwidth of the pipe and then utilize that bandwidth. There's another test that's more interesting. It's a TCP cross-traffic test. In this test, we attach two more Docker containers to the setup I showed before, an iperf sender and an iperf receiver, and they generate TCP traffic that is competing with a QUIC transfer. If your congestion controller is well behaved, you'd expect that the QUIC flow and the TCP flow share the pipe, and each of them gets about 50% of the bandwidth. When running a test, there's a lot going on in the background. First of all, the QUIC interop runner generates one or multiple random files. These files have random file names and random file contents. It then mounts these files into the QUIC server Docker image, and the QUIC server is then expected to serve those files when the client issues requests for them. We then generate a list with URLs, and this list of URLs is passed to the client Docker image as an environment variable. The client is then expected to issue requests for these URLs and download the associated files. The test is completed once the client's Docker container exits. We then check the return value of the client to see if the client thinks that the test was successful. But we don't trust the client, we can validate it. So we go and look at the files that the client downloaded and see if they match the files that we gave the server in the first place. Then, depending on the test case, we go to the simulator Docker container and look at the PCAP that it recorded. For example, for the zero RTT test, we can check if the client actually sent zero RTT packets to make sure that the zero RTT feature was used and the client didn't just download the files using a regular 1RTT connection. Let me now show you the QUIC interop runner in action. All the actions of the interop runner are controlled by the run.py script, and it comes with a few command line flags to control the execution. Let's say we want to run a test between a QUIC client and a QUICly server, and we want to run the handshake test case, we want to run the retry test case, and the zero RTT test case. What the interop runner does is it looks up the QUIC the QUICly in the list of implementations, which is in the implementations.py file here on the right. And this file contains a list of all the implementations that are currently participating in the interop runner, and each of them has a URL. And you can just run a Docker pull to get the latest version of that implementation. So the test has now completed. You can see that the handshake test succeeded and that the retry test also succeeded. And the zero RTT test is shown in gray because apparently one of the two implementations doesn't support that test case. Every implementation on the QUIC interop runner is able to tell which test cases it supports. So when we add a new test case to the interop runner, it will first show up as gray for all the implementations that haven't yet added support for that new test case. During the test run, the interop runner saved a bunch of log files to this directory. Let's have a look what's actually in there. It created a new folder for every test that ran, and that was either successful or that failed. And in this folder, we have, first of all, we have an output file from the interop runner. First of all, we have the output that was generated from booting up the Docker containers. So here at the end, we can see the client exited and the other containers were stopped. And then the interop runner goes and starts validating the transfer. So first of all, it checked the downloaded files, and apparently downloaded files matched. So we get a succeeded here. And then the interop runner looks at the PCAP, and it extracted this token. And it also checked that the client then used this token for the next transfer. Implementations can save log files to a predefined directory within the Docker container. After the interop runner has finished the run, it will copy the log files from those directories and make those files available for later debugging. For example, you can see that quickly recorded a log file here. And this is the quickly log format, but let's say something went wrong in this transfer, then quickly developers could probably figure out what was going on. The interop runner also saves the PCAP files that the simulator records. We can now open this file with Wireshark. So here we can see all the packets that were exchanged, initial and then a retry and another initial. A lot of implementations also record an SSL keylog file. This is by no means mandatory, but it can be helpful to load the keys into Wireshark to see what's actually going on. I've now loaded the keylog file into Wireshark, and Wireshark is now able to decrypt all the packet numbers and show us the packet contents of all the QUIC packets. Many implementations also record qlogs to be able to use tools like QViz to analyze the transfers. Adding new test cases to the interop runner is actually quite easy. Let's have a look at the retry test case. So in the beginning, the interop runner generates one random file of 10 kilobytes. It then runs the test, and after the containers have returned, it executes the check function here. First of all, it counts the handshakes, and we expect exactly one handshake. It then checks the QUIC version, and it compares the files. And if those match, it goes on to validate the trace. It first retrieves all the retry packets that were sent from the server and extracts the tokens from these packets. And if there were no retry packets found, the test fails. It then looks at the initial packets that were sent from the client, and it checks that the token used on those packets actually matches the retry token that the server sent earlier. In order to make this work in a normal development workflow, we don't want to require implementers to publish a new image every time they make a change to their implementation, just to try out something that they have programmed locally. Instead, the interop runner provides a flag to use a local image. Let me demo that. So I have a QUIC Go implementation here where I made some changes on the retry mechanism. And I'm building a Docker image, and the tag of this Docker image is QUIC Go local. I can now run the interop runner with a QUIC Go server, and I want to use a QUIC Go client and a quickly client. And I run the retry test. And instead of using the normal QUIC Go image from Docker Hub, I replace that by QUIC Go local. The interop runner has now returned, and you can see that the test using a QUIC Go client and a QUIC Go server was successful, whereas the test with a QUIC client has failed. This is a kind of test failure that would have been hard to catch within the unit tests in QUIC Go, but it's immediately obvious when looking at the interop matrix. I've shown you a few runs of the interop runner now, and you might have noticed that generating the results has taken about half a minute. And this is although we just ran a few tests with a few implementations. To generate the whole interop matrix with all the implementations that are currently on the interop runner, you would need about 24 hours. Few people are willing to wait for that long when running the tests locally. That's why we set up a dedicated server that runs the interop tests. It pulls the Docker images of the participating implementations and then generates a full interop matrix. Here's the result page of the interop runner. In the columns you have the server implementations, and in the rows there are the client implementations. So you can see there are a lot of successful tests, but there are also occasional test failures. Each test is linked to the log directory that I showed you earlier, and you can go here and browse the files and see what's going on to debug what the test failure was. The interop runner doesn't only allow you to access the current run, but you can also select an earlier run and see if any change that you might have made to your implementation in the meantime has changed the test results. For the future, we hope that more implementations will provide a Docker image and join the interop runner. We will also implement new tests to get an even more comprehensive coverage of the QUIC features.